Problem statement. The surface of a 50 millimeter diameter thin wall tube is maintained at 100 degrees C. In one case, air is in cross flow over the tube with a temperature of 25 degrees C and a velocity of 30 meters per second. In another case, air is in fully developed flow through the tube with a temperature of 25 degrees C and a mean velocity of 30 meters per second. Compare the heat flux from the tube to the air for the two cases. Okay, a little bit schematic of our problem here. We can consider a tube. Here's our tube. And we have two cases. In case one, we have a cross flow. Velocity here is given as 30 meters per second, and T infinity of this cross flow is 25 degrees C. This corresponds to an external flow. In case two, a similar flow condition is introduced in the form of an internal flow. So we have the fluid is air in both cases. In case two, I also have air which enters this tube in a fully developed condition. So I have an average velocity of 30 meters per second and a mean temperature of about 25 degrees C. So as you see, there is similarities between two cases, like the average velocity is the same and the temperature of the flow is the same. We want to figure out how the heat flux is compared between these two situations. So let's start with our assumptions that we need to make. So assumptions. First, we're going to assume that the situation is a steady state. For both flows. We consider that the surface temperature of the cylinder is constant and uniform. So uniform Ts on both sides. We can well assume that the thickness of the tube is negligible because the problem statement says it's thin walled, so uniform temperature on both sides. Assumption 3, we're gonna assume fully developed internal flow, and this is coming from the fact that the problem statement says so, that the flow is fully developed internal. Fourth assumption that I'm gonna make here is considering a long tube. So we just assume that length of the tube is much larger than diameter, and we will know why this is an important assumption to make. So next step is to figure out the properties. So the properties needs to be found for air, and the temperature at which we're going to try to find the properties is an average temperature, so 100 degrees C plus 25 degrees C divided by 2. This is we're trying to look up the temperature at this, look up the properties at this temperature. So using table A4 in the heat transfer book, the following properties are found. We have the viscosity that equals equals to 19.51 times 10 to the minus 6 meters squared per second. Thermal conductivity is 0.029. Unit is watts per meter Kelvin. And finally, I can look up the Prandtl number for air at this condition. Prandtl number turns out to be 0.702. Okay, once we have the properties at the average temperature, we can go ahead and solve the two cases. We start with case 1, which is the external flow. So in order to know what kind of correlation we can use, we first need to find the Reynolds number. So we find the Reynolds number of the external flow using the definition of Reynolds number. So we'll have velocity times diameter over viscosity. This turns out to be 30 meters per second times 0.05 meter over 19.51 times 10 to the minus 6 meters squared per second. If you solve this, the Reynolds number will be 7.69 times 10 to the 4. So apparently this is smaller than 2 times 10 to the 5, which is the critical Reynolds number for flow over a cylinder. So the flow is in the laminar regime. If you go back to the list of correlations for the external flow, we found that there is one correlation that covers a wide range of properties, and that's Churchill-Bernstein relation. So from Churchill-Bernstein for external flows, we know that the relation gives us the average Nusselt number, and it's pretty long equation. 0.3 plus 0.62 times Reynolds number raised to power of 1/2, Prandtl number raised to 1/3. The denominator here is 1 plus 0.4 divided by Prandtl number. This is raised to 2/3, and the whole denominator is raised to power of 1/4. And this should be multiplied by another term, 1 plus Reynolds number found with D as the length scale over a constant 282,000. This is raised to 5/8, and the whole bracket is raised to 4/5. So we have this correlation which we can use for the external flow for case 1. If you plug in the numbers, Nusselt number, we have Reynolds number equals 7.69 times 10 to the 4. We have Prandtl number that equals 0.702. Using this along with the definition of Churchill-Bernstein, average Nusselt number for this situation will be 180. Now, in order to find the heat flux, we need to use this value for average Nusselt number to find average convection coefficient H bar, which is defined as K over D times average Nusselt number. Now we can plug in the values that we have for properties: 0.029 watts per meter Kelvin divided by 0.05 meter, that's the diameter of the tube, multiplied by 180. This is going to be equal to 104 watts per meter squared Kelvin. This is my H bar of case 1. So we box this one, so we're going to go back to it. Now we can also find the heat flux. So knowing the convection coefficient, heat flux of case 1 will be simply H bar of case 1 times Ts minus T infinity. H bar 1 is 104. This is watts per meter squared Kelvin times 100 minus 25 Kelvin. And finally, my heat flux of case 1 will be 7,840 watts per meter squared. Let's box this one as well. Okay, this case 1 dealt with the external flow. So we found the average heat flux from the external surface to the external flow, and the heat flux from the external surface to the external flow. Now we're gonna go and take care of second case, in which heat is now transferred from the inner surface to the internal flow, which we call case 2. So we kind of wrap up case 1 here, starting case 2. Internal flow. Again, we have to find Reynolds number for this case. So Reynolds number will actually be very similar, or actually exactly equal to the value that we found for the external flow, and that's due to the fact that um that you see in the definition of the Reynolds number for internal flow is equal to the velocity of external flow. So I can simply replace it with Vd over viscosity. Make sure you notice that this only happens in this specific problem. It's not always like that. So it's going to give me exactly same Reynolds number. Now the difference is, for an internal flow, this Reynolds number is more than 2300, which makes the flow turbulent. Now we have to find the right correlation that we can use for fully developed internal flow into turbulent case that gives us the average convection coefficient. So we have one correlation for fully developed turbulent flow, and that's the following equation. It's called Ditus-Boelter correlation. This is equation 860 in the book. And I'm gonna write it here for your reference. This correlation is giving you the local Nusselt number as a function of Reynolds number raised to power 1/4 and Prandtl number raised to power of n. There are certain conditions in order to apply this this correlation. First of all, n is gonna be 0.4 if Ts is larger than T infinity, or n is 0.3 if Ts is smaller than T infinity. And since in this case T surface is larger than T infinity, we're gonna have n equals 0.4. The other conditions associated with Dittes-Boelter are Prandtl number should be between 0.6 and 160. This is also met because my Prandtl number is about 0.7 in this problem, so this condition is met. Another condition for this correlation is Reynolds number found with D as with diameter as the length scale should be larger or equal to 10,000. And we figured that it is actually more than 10,000, so this condition is also met. And finally, the last condition is L over D should be larger than 10, which in our assumptions we assume that L is much larger than D, so this condition is also met. So now that we have this correlation, we're going to use that to find the local value of convection coefficient. But since this is a very long tube, so for a long tube, it's safe to say that average Nusselt number is equal to, almost equal to local Nusselt number for fully developed condition. In fully developed region, we can write that. Therefore, this shouldn't actually include this, so this is just a local value. So continuing here, I write Nusselt number, average Nusselt number equals local value of Nusselt number, and this local value is found from the correlation that we just discussed, Dittes-Boelter. Now we plug in the values that we have, 0.023, Reynolds number is 7.69 times 10 to the 4 raised to 4/5 multiplied by 0.702 raised to 0.4. So what we will get is an average Nusselt number of 162. From here, as usual, we can find average convection coefficient, K over D, Nusselt, plug in the properties, 0.029 watts per meter Kelvin, 0.05 meter, and I will have an H bar of 94 watts per meter squared Kelvin. This is for case 2. Now we also wanted to find the heat flux from Newton's law of cooling. So heat flux of the second case corresponding to the internal flow is H bar of the second case times Ts minus Tm. Tm Tm is the flow temperature, of course. And we have just plug in the values, 94 watts per meter squared Kelvin times 100 minus 25 Kelvin. From here we will have a heat flux for the second case of 7040 watts per meter squared. So comparing the two values, we'll see that the numbers are actually pretty comparable.